Thank you all for coming. And Tony Marie and the previous speaker have given a very nice, set a nice stage for all the overview of this project and the overall of the science of the broad carbon. But now I'm going to go to a little bit detail of the greenhouse gas emission, how we measure the vertical flux. We have seen, you always seen, this is a really collaborative project involving the scientist, stakeholder, and the end user. And even within the scientist team itself, it's also highly collaborative. We see a lot of name here about the vertical flux, and also it's involved in multiple institutions. People have different background, different discipline, but we all work together to understand the broad carbon from science point of view. And of course, we all know this is funded by the NOAA National Asteroid Research Reserve System, and we also have a lot of other collaboration, including NER, webinar staff, and other people all involved in this science. Let me just skip quickly this acknowledgement. The overall project of this piece, this is one of the pieces of the science. For this piece, to try to understand, quantify the carbon dioxide and the methane fluxes vertically from the small point, or we call the chamber measurement, or scaling up to the annual accumulation of the carbon flux, and eventually we try to understand the whole ecosystem, how much greenhouse gas emitted from that system. And we here, for this talk, will focus on the carbon dioxide and the methane. We also, of course, have a nitric oxide measurement, which we try not to cover, try not to cause confusing for this talk. So we'll focus on the carbon dioxide and the methane. The second is try to understand the driver of those greenhouse gas fluxes, including how temperature, light, and the tide and salinity drive the change of those gas fluxes. Eventually, this information will be imported for the modeler. Omar will present later on about how to develop a sophisticated model to capture or to simulate those gas fluxes. Finally, we try to assess the impact of anthropogenic nitrogen loading on the carbon sequestration and the net greenhouse gas emissions. So this is I try to explain more about, we're talking about a lot of blue carbon and carbon sequestration, but how we can really quantify the amount of blue carbon or sequestration rate from the wetland. So I have to explain, walk through a little bit of detail. For the blue carbon, I just tried to add another terminology. We don't know that, but we don't happy. But we want to add a new called net ecosystem carbon balance. The idea is what we are talking about is really understand the net carbon balance, because carbon is dynamically changing. It's not one direction of change. It's dynamic change. So involved vertical in and out. Particularly, let's look at, I don't have a point here, but look at the red line, R, which is called respiration. Respiration of ecosystem respiration involved both decomposition of CO2 from the soil, from sediment, and also plant respiration from those saltmarsh plants. So that is up, and the green arrow indicates in, which is we call the GPP, which stands for gross primary production. It's a sum of photosynthesis. So in the vertical, there's carbon in and carbon out. So we want to understand the net result of carbon in and out. And also we have the methane flux, which is the purple line here. We see the CH4, which is methane flux. There's a methane flux released from the system. And of course, there's an exchange of the carbon through, we call the lateral flux, FL here. And the lateral flux is also very, very complex, involved of the change of the DOC, dissolved organic carbon, and nitrogen as well. And later on, we have speaker Kevin will cover that. So for me, I'm going to focus on the three vertical lines, which is the emission of carbon through the respiration R, and optical carbon through the green arrow of photosynthesis, and also the release of the methane. So all those carbon is dynamic changing. So residue, the net flux, will influence of the carbon stock. I put it here as a carbon stock. So overall, there's a change, dynamic change of the carbon. So the net result will be carbon stock. So we have to really keep in mind, when we talk about carbon, we're talking about carbon stock or the pool or the carbon flux, which is change of those gas fluxes. And also some of the dissolved liquid phase of the exchange of the carbon. So there's two terms, again, it's carbon change with carbon flux, and the other is carbon stock. But we know that the flux change really influences the final result of change of the pool. So what we know, we can know both basically. We want to know the change of flux, we also know when the change of the pool. So in the right panel indicate the human influence or measurement will eventually change all those pool and flow. For example, we add a nitrogen or different nitrogen loading will change those carbon pool, or we restore the new system or ecosystem, or we make conservation of the coastal wetland. Those pool and those flux will eventually change. So we are talking about a very complex system, so we have to really use a system point of view to understand those change of the pool and fluxes. So there's a final kind of thing, NECB, basically is we try to use this term to quantify the change of the carbon flux or carbon credit, which is a change of dc dt means the change of the pool. Basically, the rate of change of the carbon stock is defined by the NECB, which is net existing carbon balance. And we can calculate by those terms. So give you more slides showing, okay, the method. After we understand the dynamic change of the system, so how we can use some method scientifically to quantify those systems. There's basically three methods. Number one, we can using the flux measurement. Fortunately now we have the very sophisticated system or technology help us to really understand the change of the fluxes. So the direct measurement of flux help us understand the mechanism and process underneath of the change of the fluxes. So we are using the NECB term, which is what I mentioned, is a dc dt, which means the change, dt is time. We change of the carbon pool over time, which we can also measure by the NEP, which is a net ecosystem production, which indicates the net result of GPP and R, with NEP here, and also the change of the flux of the methane, and also net flux with FL. So for the NEP measurement, which I will focus on, that we rely on either chamber measurement and the other we call the eddy flux measurement. There's a poster here showing how we can using the new technology called eddy covariance-based measurement. You can automatically measure the existing carbon exchange. We can also use the chamber, which is smaller, but it's more nimble, it's more flexible. We can move around to understand the vertical carbon exchange. That's the number one method. The second is we can measure stock. Basically, we can use a long-term sediment core and to measure, understand the carbon stock and how they change over the year. Basically, the unit is over the year versus flux is we're talking about unit of per second or per day. So we can see both these two, stock and flux, they should be comparable. So eventually, those two numbers can be comparable and they can match each other. And then we can use modeling. We have we'll talk about modeling later on. Another speaker can talk about that. And how we can develop a model, which basically is a very relatively inexpensive way to understand the carbon flux and the carbon credit. But all the model we know, we have to use those data to develop the model and also use those data to quantify or validate those models. Those are basically the three methods help us really understand the carbon and eventually develop methodology and develop economic analysis to deliver the message to the stakeholder. So study site, we have covered this is near the Fue Bay area, and we have a high nitrogen and low nitrogen and mid nitrogen and no nitrogen area here. And we select 4 sites across different nitrogen loading. But I have to tell you, even though we're talking about it's in the Fue Bay, it's in the Cape Cod, the nitrogen loading overall is small. It's about 1 to 10 grams of nitrogen per square meter per year at that level. So there is gradient, but overall the range is not very high. And we designed a very sophisticated, very good boardwalk and all the way across the site. And we select a sub kind of plot and make the plot-based measurement of the greenhouse gases. We made a bi-weekly measurement across 2 years, 1.5 years, And then in the winter season, we make about monthly measurement of the greenhouse gas cross system. So we spend a lot amount of time to go to field, make those gas measurement. And I can show you quickly, we have a long boardwalk, basically designed and developed and built up by the webinar staff, particularly Jim Russman and the other people, and design the boardwalk and then help us really bring our sophisticated, state-of-art of analyzer to the field without impact much of the system. And then the instrument really can help us to to make the measurement instantaneously. Previously, we can only make a measurement use some of the gas cylinder method, basically take the air and go back to lab to make a measurement. But now with those systems, we can take to the field and make instantaneous gas measurement. So that really speed up the system and allow us to get a large amount of time for a larger frequency of measurement, high frequency measurement. And this shows you the some instruments. We can put the chamber, the transparent over there. You can see the right of the up panel. This is a transparent chamber. We cover in the Marsh, and then the chamber, we take the air out and connect to the analyzer, and then we can really make the instantaneous measurement. And this some raw data, just show you quickly, because of this instrument, because of this, we developed those assembled system so that we can get continuous, basically high frequency measurement. We can get CO2. When we covered, you can see CO2 line goes down, which indicates uptake of the Marsh. And when we release the chamber, the concentration goes back, and we see the ambient, mix of ambient in the chamber. Then we cover it again, the concentration goes back. So it's a lot of straight line then showing the high sensitive of the system. And same thing as below the panel of the figure showing the methane flux. It's going up and down. Going up means when your chamber covered, there's a methane flux come out. So we can make the measurement and make a calculation, and then we open the chamber. Then we'll go down. Here's some quick equation. Basically, we can calculate the flux, use those measurement of the chamber, and eventually we can calculate flux based on the changing rate of the gas within the chamber. So I'm not going detail. Here's some of the result. And for the right panel, you can see, okay, here's a red line indicate of the respiration. The respiration are basically the CO2 emissions form the line, and the green line indicate the total net, or called the net NEP, net ecosystem production, which is net result of the two lines of the red and the blue. So that's the indicator of the net flux of the CO2. And the bottom is CH4 net methane flux, and we also see the seasonal pattern. And the x-axis is the day of year, which is Julian day, across the season in 2014. So basically, we can quantify the change of the gas flux, both CO2 and methane, across the season. So from this line, we basically can calculate total amount of carbon emissions of CO2 and also the emission of methane. So the left panel, we see the basically sum up of the carbon balance across the year. So this is the unit is gram of carbon per square meter per year, so which is equivalent to the other system. Basically, it's measurable it's comparable with the other system. So the total, I just give you a number, NEP, we estimate of the net carbon result is about 380 gram of carbon per square meter per year at that level. And then there's a lateral flux, which is still developed, but it's about 200 level. So the total amount NECB, basically the net barrier, is about 160 of gram of carbon per square meter per year of that amount of carbon buried into the soil marsh, into the sediment. So this number is also comparable with the sediment core that you will see the report later on. So the idea is, based on the gas measurement, we can calculate total sun and we can estimate all the errors. We also make the measurement of the carbon flux across the nitrogen gradient. We already introduced you of all the 4 sites. So now we can get all those curves across the 4 nitrogen gradient sites. including above the low nitrogen, and the bottom one is high nitrogen site. We see that overall the shape is similar, but each side there's a slight difference in terms of the CO2. But overall, when we compare together, we do not find a significant difference across all the sites. Even though only one side, the yield pump, the right and the lower panel, the carbon flux is a little lower across the 4 sites. And here is the methane flux. Methane flux across the 4 sites. And the bottom above one is about 2 is a low nitrogen, and then the bottom one is a high nitrogen site. We also make comparison across the 4 sites. We found overall there's 2 sites, the Haberlin side, which is low nitrogen, that the methane flux is a little bit higher than the average, and the yield pump in the lower in the corner, right corner, that the methane flux is a little lower than the other average of the other 2 sites. So the reason behind that, we figure out, is probably primarily induced by the salinity. We will see the model, you will see the whole model development. The salinity is a major driver for the methane. But now we also try to do more of the work, try to understand how the methane flux change with salinity. So we are now trying to find the even longer the salinity gradient to understand how the methane flux change with salinity. But so far, we have number to quantify this. So more detail, we are still working on that, understand the relationship between the flux, methane flux, and the salinity. So in summary, we do find that the Saltmarsh is a significant carbon sink, and we can quantify how much carbon stay there based on the gas measurement. So the idea is, or the result is, that if we do restoration or conservation, that this carbon sink will be significant, be installed, or be significant to the social benefit for the future carbon credit. And the methane flux in this Saltmarsh is about 3 orders of magnitude less, smaller than the CO2 fluxes, primarily driving the salinity in the Saltmarsh. If you go to fresh wetland, the methane flux will be dramatically increased. But in this, it's about 3 orders less. Even though we calculate the global warming potential, we multiply by 30, still is small for the methane. So the final thing is, we found that those carbon flux is driven by the light, solar light, and salinity, tide, and temperature. Those small amount of nitrogen loading, we are talking about the 1 to 10 of that unit. We do not find the big significant change in terms of the carbon fluxes. So we still have time. I'll be happy to take questions. Thank you. Yeah, that is very time consuming. We have 3, it's kind of experiment design. We have 3 plots, and each plot we have 3 locations. So we make a measurement for spatialists, and then we average all the plots to get those 1-point measurement over this time. Then every 2 weeks, we go to field and make a similar measurement so that get result. So that we can have both spatial coverage of the spatial replicates, and also we measure across the time over the season. Then we can get the whole curve or seasonal pattern of those flux number. Yeah, we have spatial replicates, basically called the different, basically cover the spatial heterogeneity, but also we measure across the time.
So this project has been 4 years. If you noticed a interannual variability of the CO2 and the methane?
Yes, this is 4 years, but we spent 2 years in the field. So yeah, we see some difference, but for interannual variability, we need a longer time period to do that. So that's another thing. The idea is we try to use a model. If we understand the major driver there, and then if we know the weather, across time, eventually we can predict the future. If we really identify the major driver of the environment driver. So basically, we now identify the 4 of the factor as a major driver to see the change of the seasonal pattern. But eventually, we hope those can be incorporated into those predictive model so that we can understand more either in the future or in the past, and also quantify the inter-annual variability.
A great talk, Jim. So this is Alec Wang from Wusko Oceanographic. So the number you're showing there, 160 gram carbon, is that more than 10% of your GPP number? And I remember back in the early years when Chuck Hopkinson and Giblin doing their research and some of the marshes, I think it's less than 10%. So how does 160 compared to some of the early estimates in terms of the net ecosystem barrier rate or the stock carbon? I mean, is there? I think Bob is here, maybe more familiar with me, but is this some kind of higher end of barrier rate?
Yes, that's a good question. So far, actually, in the wetland, coastal wetland, we don't really have the good number to really make comparison. Additive flux system is just being installed by some of the system, and some of the methane flux not really being quantified very well, and even lateral flux, I don't see any publication really. They conducted those kind of system point of view to understand the both vertical and the lateral flux. We haven't seen so far any. I think we are comfortable that this is first study really show those complete story of the exchange of the carbon from the comprehensive way to understand the system. So we don't have any kind of baseline information we can use for compare. But this is kind of one of the, I think we are the earliest one to report. Maybe some people don't agree, but we just say this is a kind of, it's no comparison. Yes, some of people report some of the data, but it's partial story, particularly, for example, GPP and NEP. But we incorporate all the other information, like lateral flux, into consideration. In a terrestrial system, we can compare with other terrestrial systems, but I think this number is comparable, particularly those, the final kind of carbon barrier data, which is higher than many of the terrestrial systems that people believe that in wetland is higher. I think those are comparable. And also GPP. GPP data is comparable with most terrestrial systems.
This new estimate, at least to me, is surprisingly high, which may indicate that in the past we may significantly underestimate this carbon stock. At least to me, I think this is something new. I first see this kind of percentage here. So
yeah,
thanks.
Hopefully that is the whole idea of this project, try to kind of push the boundary of the science in this field. Thank you.